As we begin 7.8 here, we're going to take a look at an idea that's not all that intuitive. We're still looking at matrices, and we're going to examine the idea of a determinant. Now, math is a language, and when we're learning the basics, a lot of that language can be pretty intuitive. But as we get more and more complex, sometimes the ideas that math can discover are not all that intuitive. And this is one that I don't think would naturally be that way. This is a man-made construct, I guess you could say, of taking a matrix and dividing the diagonals, or I'm sorry, multiplying the diagonals and then subtracting them. So we're going to take this diagonal, multiply A and D, and subtract the other diagonal, C times B. Now this creates a number. Now, I'm sure there are many applications of this. What's interesting is the math turns out to be very helpful as we move forward. You'll see that in this section and the next. But who thought of this and why is beyond my scope here. I don't know. But one thing that it is often used is in encrypting. And I think I can kind of see why that would be the case. You can encrypt a message by using the value of the determinant because it creates a unique number as you multiply through. So a way to hide a message could be exacerbated or intensified by using the matrix as you multiply across. So again, I don't pretend to know all of how that exactly works, but I think I can kind of see that in the abstract. But let's talk about what a determinant is, like work a few of these, and we'll begin to see that how to do it, and then we'll begin to see how, for some reason, if you look in the language of mathematics, it begins to have some applications that I would not have known. Now the first thing we need to know here is if you see these absolute value bars around a matrix, this isn't the absolute value. What this is referring to here is the determinant. So let's take a look here. We're going to find the determinant of this matrix. Well, what we're going to do is we're going to multiply this diagonal from left to right, and then we're going to subtract the multiplication of the other diagonal. So we've got the determinant here. We put it in these absolute value bars to say we're finding the determinant. Multiply the 5 and 3 minus the negative 6 and 2, and we get 27. Okay, so that's a quick lesson here on what a determinant is. Very quick, I know. Now, one of the applications here is that Cramer used the language of mathematics to discover that he could solve systems of equations using determinants. Now, this is actually not terribly hard to see. I'll leave the proof, it's in the book, but the story behind it is this is actually just being solved for using the elimination method. Solving for x and y using elimination actually is how he created these formulas. So I don't think the formulas are beyond our ability to see them, but it is getting more and more abstract. So if you want to see that proof, he's really just doing the elimination and solving for x and y, and saw that these definitions he created are the determinant. So he saw that it had some value. But here's how Cramer's rule works. If we saw a matrix, so here down on the bottom here, here's our normal matrix for this system. So we've got A1, A2, B1, B2, and then we're not going to augment it. We're going to leave the solution matrix over here. Well, that's what D is, just simply turning this into a matrix. Now, the top, this D sub x, is going to be that same matrix, but in the x column, which happens to be the first column, we're going to replace those coefficients with the values of the solution matrix. So look what's happening here. We're taking A1 and A2 and replacing them with C1 and C2. Now in the second one, if we want to solve for y, the bottom matrix is just our normal matrix, and the top matrix is going to replace the solution matrix, or the y coefficients with the solution matrix. So let's try one here, and hopefully it'll make a little more sense. So first of all, let's find that bottom matrix D. So D here is just going to be the coefficients, 12, 2, 13, or 3, negative 3, just the standard. Okay. Now, what about D sub x? Well, it's going to take the original matrix and it's going to replace the x coefficients with the solution matrix. It's going to replace them with 15 and 13. So we've done that here. Now, see the same here on the bottom. We've got D as just the basic matrix. D sub y is going to replace the y coefficients with the solution matrix. We've got this here. Okay, Now, they're in these absolute value bars, so this isn't the true matrix. They're looking for the determinant. We want the value of the determinant. So we multiply this diagonal, get negative 45. We subtract the value of this diagonal and get negative 39. Do the same down here, multiply these, we get negative 36. Now we're going to subtract the value of these guys multiplied, which is 6. Okay, so we tidy these up here, we get 2. We do the same game here. This times this gets the 156 minus this times this. We found the determinant of the top there. Now we go here and subtract that. Now we tidy this all down and we have the solution to this system of equations. Again, we have lots of methods to do this, but here's another one. And again, not so intuitive, but it really is actually just being solved for the elimination method, and generic form is how he came up with Cramer's rule. Okay, so let's try one on our own here. So the first thing I'm going to do here is find D. Well, I should probably just we're going to leave these as absolute value bars. So this is we're going to find the determinant of D here in just a second. So now, do I want to do these each individually? No, let me just go for it here. So x is going to be, so D sub x is going to be this matrix, but the D column is going to be replaced with the solution matrix. So I'm going to do negative 11, negative 13, 2, 1. That's the top. Now the bottom here is going to get us this. Now come over here, I'm going to do y. So y is going to take that same matrix, and it's going to replace the y column with the values of the solution set. And we're going to divide it by D. Okay, so now let's find the values of these determinants, and we've got our solution. So this diagonal gets me negative 11. Now we're going to subtract this diagonal, which is negative 26. Now we'll do the value of D. That's going to get me 1, and this diagonal, we're going to subtract the value of this diagonal, which is negative 4. Okay, 26. So this turns into positive 26. 15 over 5 gets us 3. Now we'll do the same up here. So the bottom is going to be the same because that's just D again. So this is going to be 5. Now up here we're going to get negative 13 minus 22. So this diagonal minus this diagonal, and that's going to be negative 35 over 5, negative 7. So we could have used any of the approaches we know. We would get the same solution, but Cramer's rule will get us there as well. By using determinants, we found the solution of this system of equations. Oops, 3, negative 7 there. Okay, now defining the determinant of a 3 by 3 matrix is much harder. So it was very simple for a 2 by 2. But when we do it for a 3 by 3, what we're going to have to do, we're going to need these diagonals, and it's not so simple. So what we do is we're going to repeat the first 2 columns. We're going to add them on. Look how they've augmented the matrix by adding the first 2 columns again. And the reason is we need to do the diagonal, but we need to make sure we hit all the numbers. So we have more diagonals. We're going to do this one. It's right here. Now we're going to go through and make sure we've done all the possible diagonals. This time we're going to add all of the downward diagonals. So we're going this way, we create this. We're going here, we create this. We're going here, and we create this. Their number's wrong. Yeah, I don't know if their number is going to turn out wrong. There are often mistakes here. This one is off. It should have been. Oh, no. This is right, and this is wrong. That should be a 0. If they repeat the first 2 columns. So this is right. Should be a 0. Okay, so we're going to do all those diagonals, and now we're going to subtract all of these diagonals multiplied together. Okay, so we have some more work to do, but that's the same idea. We're just going to augment it with the first 2 columns repeated, multiply all the downward diagonals, subtract away the product of all of the upward diagonals. Put that together, and there's our value of a determinant for a 3 by 3. So pause this if you want to try it yourself. We're going to add. We're going to augment this with the first two columns repeated. So now we're going to do our diagonals. 1 times 1 times 3 is going to give me 3. Now we're adding when we're going down on these. So negative 3 times 1 times 1 is going to give me negative 3. 7 times 1 times negative 2 is going to give me, so plus negative 14, however you want to think about that. Now we're going to subtract all the upward diagonals. So I'm going to subtract 1 times 1 times 7. I'm going to subtract negative 2 times 1 times 1. Oh, my pen has disappeared. It's probably not, I would not normally write it like this, but just to show you what's happening here, I don't want you to be confused by what's happening. So we're subtracting the value of negative 2 times 1 times 1, 3 times 1 times negative 3. So we're subtracting away negative 9. Okay, so I did all these double signs again. I'm going to get rid of them. I just wanted to make sure you understood the formula. Okay, so this is really what we're doing. So I have 3 and negative 3. This is going to give me negative 21. So I've got negative 21 plus 11 is what I'm down to, so negative 10 is the value of the determinant. So again, we repeated the first two columns. That created 3 downward diagonals and 3 upward diagonals. We add them down, and then we subtract the 3 that are going up. Okay, now Cramer's system can be expanded to a 3 by 3 system. It's not going to change anything. Let me just show you. I'm sure you'll see. So D is just going to be the matrix without the solutions, just the normal matrix, the coefficients from the equations. Now D sub x is going to replace all the x values with the solution column right here. D sub y is going to subtract the coefficients in the y column with the solution column. And then D sub z is going to extend that idea. We just now have a third one. We're going to replace the coefficients in the z column with the solution matrix. Okay, so now we just have 3 variables, but the concept is exactly the same. Crunch down these determinants, and we get our solution set. Excuse me. Okay, so I don't know the best way to do this. Let's do. Okay, so there's the matrix, just where we take all the individual coefficients and put them right there. So just we made our regular matrix. Now, the D sub x matrix, which goes on top for the x solution, is going to replace the x column with 13, 1, and 4. So 13, 1, and 4. Now everything else is going to be the same. Okay, so and then finally z would be okay, so there's our determinants. So doing these 3 by 3 are rather challenging. And this would probably not be the ideal way to do this, especially since we know how to just redo echelon this matrix if we augmented it. So there's so many approaches that would be faster than this. But that said, this will work. Now I'm not going to crunch all these because for 3 by 3s we'd have to add the extra 2 columns, go diagonals each way, and technology would help too. So there's so many other ways to do it. But here's the setup. Now I'm going to pause this real quick and just get the solutions if you want to try crunching this on your own. Give me 1 second here. Okay, so I paused this in order to get the solution out of the back of this. So again, to solve these, you'd have to, because they're 3 by 3, we'd have to repeat the 2 first columns, do all the diagonals. It'd be very time consuming. So again, we know other methods for solving this. We could have done just a reduced row echelon matrix on our calculator. But if you tried to do this and wanted to do all these by the determinants, here's the solution that you would get. Okay, now before we conclude this section, we got to take a look at some systems that break. So we've seen before that we can get, it's possible these are lines, and it's possible they don't intersect, or perhaps they intersect on top of each other and have either. So we could have no solutions for parallel lines, or infinite solutions if they're on top of each other. So with Cramer's rule, here's what happens. If you get a determinant, and the value of a determinant is 0, then you have an inconsistent system. You don't know whether it's no solution or infinite solutions. So a determinant that turns out to be 0 is one of those broken kind. There's no typical solution. But the problem is the matrices determinant can't tell us which of the two choices it is. So if you come across the determinant that equals 0, then we've got to go ahead and do it old school, which would have been just to do it the methods we've learned previously. We would do elimination here, and we'd find out we get 0 equals -8, which is not true. So this was no solution. So if you get a determinant that equals 0, you've got to stop. You know it's one of the two odd solutions, the unusual solutions, but you can't tell which. You'd have to go back to substitution or elimination. So if you graph these, turned out they were parallel lines, and that's why they were no solution. Okay, let's try this with a 3x3 system. And so the same thing, if you add the two columns, repeat the first two, did all your diagonals, and then subtract the upward diagonals, you get a determinant of 0. And the determinant of 0 means this is either no solution or infinite solutions, and the matrix approach can't tell us. So we'd have to go back to good old-fashioned elimination, and we get down to 0 equals 0, which is true, so we have an infinite number of solutions. Okay, so that's your introduction to determinants and to Cramer's system. And again, it has value. It would definitely have value as you move into more higher advanced problems. For us, it just seems like another approach to do some things we already know, but it is interesting that it does work. And again, it has some higher applications.